Hello, everyone, and welcome back. We're going to be talking about section. Don't worry about drawing these things right here. This is not something that you need to write down. This is something for a little bit later, but we'll get to it in a second. So section 1.4. Which is right triangles and trigonometry. And in the future, I'll make sure I save that one, guys, and we can work on that one in like a little break if you want to join in on it. I'll save that one. I won't let any of my other classes do it. I'll try and have one for every class. One thing to know about crosswords, by the way, if you do decide to get into it and you want to use the New York Chimes, they get progressively harder. Monday is the easiest. Saturday is the hardest, and Sunday is variable, but it's bigger. Sunday is always the biggest crossword. And then Tuesdays and Thursdays are usually rebus days. A rebus is where you put multiple letters inside of one box. I'll try and make sure we find one by the end of the semester. Rebuses are very fun. When you find out you've got a rebus puzzle, it's the best. It's better than anything. So anyways, so we're going to talk about right triangles and trigonometry today. We're going to very briefly touch on trigonometry. I don't think we'll get to anything of substance there, but we're going to cover all of the important parts of right triangles first. But before, in order to do that, I want to kind of review a few things. So review of what we call the additive property of equality. What is that? That's a good question. That is a way that mathematicians have tried to keep mathematics away from the pores forever. Mathematicians, sadly, from its conception, was basically designed by the upper class, and they didn't want people knowing about it. So they tried to hide it behind very, very intense names and things like that. It's very, very frustrating. And part of it is just because of how we've set up mathematics, but part of it is very, very exclusionary, and is bothersome to me. Like, you get some people who get really up in arms about saying top and bottom of a fraction. Like, you have to say, no, it's the numerator and the denominator. And just, top and bottom is fine enough. Either way, so this is one of those things that's trying to sound way more scary than it is. The additive property of equality. What it says is that if you add slash subtract, that is, add slash subtract the same quantity from both sides. Let me actually make that both capitalized. All caps. The way any argument is won. If you add and subtract the same quantity from both sides of an equation, the equality remains balanced. So when we're talking about equality, we're talking about like an equation. Something equals something else. And what the additive property of equality is, it's really kind of like an axiom of mathematics. It's a requirement of our system. It's a rule that we've set up, and it's a rule that makes sense. And when you think of an equation like a balance, like an old school balance, you don't need to draw this, but it's got like these two things. It's got a base, and then you've got these little places where you can put stuff. Do you guys remember these things? Back in my day, this is actually how we measured things. We didn't have gram measuring things, we had to do this. This is how we determine who were witches and not, like in a Monty Python situation. But in all seriousness, an equation is much like a balance, and that if you add the same thing to both sides of it, it stays level. Whereas if you add one thing to only one side, tilts off balance. Like if I only add something right here, then this piece goes down and this piece will go up, right? So what the additive property of equality means is that you can add or subtract the same thing from both sides and it remains flat, it remains level. So as long as you're doing it to both sides of the equation, you're all good. That's what that property is saying. So for example, if we have x plus 5 is equal to 3, and our goal is to try and get the x by itself, what we could do is subtract off 5 from both sides. And this is why I like the color, by the way, is this really shows that I'm doing something to the equation. This is me doing something to the equation. If I were to just write this in the same color, and you're looking back, like, sure, in the moment, we know what we're doing, but if you're looking back over your notes 5 weeks from now, you're like, wait, what's going on here? So that's why I like adding color. But the reason why I'm subtracting 5 is because I want to get that x by itself. And that 5 is being added to it. So in order to get rid of it, I need to do the opposite operation. So it's being added, so we're going to subtract 5. That will cancel it on the left-hand side, and we get x is equal to 3 minus 5 is -2. And so to talk about what this really means, one thing that's important to understand is that this equation, so this is our original equation. This is also an equation. It's all like -2 is the solution to this equation, but it's actually a solution to both of these equations. They're both equations. And so what I'm saying, when we say that they remain balanced, I mean that the number solves both of them. So -2 solves this equation because if I replace x with a -2, I get a true statement. I get -2 equals -2, true statement. And then if I plug in -2 into this, I get 3 equals 3, also a true statement. So when you add or subtract things, as long as you're doing it to both sides of the equation has the same validity. It stays the same. It looks different, but it has the same solution. So our goal, whenever dealing with equations, is to use this property to isolate x by itself on one side to get x equals blah or blah equals x. One of the two. It matters not. There's like another example of this kind of high language that mathematicians like to use is this is the we call the reflexive property, the reflexivity of equality, in that x equals 2 or -2, you don't need to write this, is the same as -2 equals x. Right? They're the same thing. So it doesn't matter what side you get the x on by itself. It's just you need to get the x by itself. Convention, American, like honestly, European and Western culture convention is to put the x first. And I believe my theory on that is that that's how we read. We read left to right, so we like to see the variable first. I imagine in a parallel universe, if we read right to left, that it might be that we write x equal like in the backwards direction. I'd love to know if we could travel. But anyways, that is going to be our goal. So I'm going to do 2 examples. I think that should be sufficient for a little bit of a review. But if you guys need more, please let me know. So solve for x. And it's going to be, part A is going to be 5 equals x minus 2. And part B will be 12 plus x equals 15. And granted, once again, if this is a review for you, awesome, great, good for you. That's excellent. But as I said earlier on, we have a bunch of people from a bunch of different backgrounds. This might not be a review for some of you. And if it isn't a review for any of you, that's great too. But we're still going to do a little bit of practice. So solution. Part A, 5 equals x minus 2. I like to get the x by itself, so I need to get rid of that subtraction of 2. So I'm going to do the opposite operation, which means I'm going to add 2 to both sides. That'll cancel the 2 on the right, and on the right-hand side, we'll now just have an x. And so we get 7 equals x, or x equals 7, however you want to write it. Convention would be to write it that way. But I'm not going to mark it like nothing bad's going to happen if you write this 7 equals x. Part B, this one I deliberately made it this way just to be a little bit tricky because there's no sign in front of the 12. When the x is first, it's pretty nice to figure out what's the operation to do, but this is a positive 12. You could rewrite this if you wanted to as x plus 12, and that's by the commutativity of addition. Once again, another one of these like hoity-toity words to try and scare people off, meaning that it's the same back in either direction. So you could rearrange this as x plus 12, which gives us the intuition then that to get rid of that 12, we need to subtract 12 from both sides. So subtract 12. By the way, if it helps you, because I know some students can get a little bit worried where both sides start, you can draw a vertical line down through your equation, your equal sign, to say that is the wall. That is dividing one side from the other side. If that helps you, awesome. If it's unnecessary, don't worry about it. But some people like to do that to know where to make sure to subtract the 12 or add the 2 or whatever it may be. All right. And so that cancels the 12s on the left-hand side. We get x equals 15 minus 12. That is 3. And that is our answer. Are there any questions on that? All right.
Another exercise.
Sure. I've got a couple more. Thank you for asking. So bonus. We're going to solve x plus 7 equals 91. All right. Once again, the goal is to get the x by itself. The 7 is being added, so to undo the 7, we're going to subtract 7. And that cancels it on the left. And we'll have an x this. Now, just as a nifty little trick, I wanted to show you guys a little bit of cool arithmetic that you can do to become faster at mental math. If you don't want to be able, if you don't want to do that calculation, I'm sure you guys all learned the old classic, tried and true dad crying with your dad on the table while he yells at you, that whole thing, right? We all got that experience. The good old, okay, you borrow 1, and then you do this, and blah, 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 blah. There's a faster way, or there's a more clever way, and it's actually really, really cutesy. If you instead add the same number to both the thing you're subtracting from and the thing you're using to subtract, it stays the same. So why not add 3 to both numbers? To make it 94 minus 10. Much faster to do. You don't have to do any you don't have to do any borrowing or anything like that. Granted, the faster you get it, you don't really necessarily need to do that, but that's very, very useful. That's one of the cool little mental math tricks that I've learned in my time. The new math method of calculating subtraction is actually very, very cool if you've ever seen it. The way they teach how to do subtraction is actually quite clever. But I'm getting sidetracked. So the answer is going to be 84. Nifty little trick. And if you'd like to, I can show you proof of why that works. But you can do that with anything. You can do that with any problem. You can just add the same number to both the thing you're subtracting and the thing you're subtracting from, and that you will get the same answer. You're just moving the subtraction over. So we'll do one more. Let's do a nuts one. So let's do 5 plus x minus 2 is equal to 19. The way I like to think about solving equations, by the way, is imagine the x is your house and you're having a party, right? Your parents have found out and they're coming home. You found out that your parents are coming home and you need to get everybody out. You need to clean up everything. So what are you going to do? You're going to try and get rid of everybody that's not a close friend first. That plus 5 and that minus 2, let's simplify that a little bit. That's the same thing as x plus 5 minus 2 equals 19. That's x plus 3 equals 19. This 5 minus 2 is 3. And so we've kind of grouped all the problem people that we don't really know at our house party. And we're just going to try and push them out of the door because they're not going to help us clean up. That's only something you can expect from your good friends, right? They're the ones that will make sure that the house is tidy. So then we'll subtract 3 from both sides to get that 3 out of the way. And you get x equals 19 minus 3, that is 16. All right. The next thing I want to review, and it's mainly like some of the parts of the very, very beginning are going to be things you've probably already seen, but it's mainly to set up for a thing called the square root property. So we're going to review square roots. And so we've already said it out loud, and you probably already know what I mean by it, but just to write it out in full detail, to square or squaring a number means multiplying the number by itself, i.e., raising to the second power. That's what squaring a number means, is to raise it to the second power, multiply it by itself. So 2 squared, if we're going to square 2, that's going to give us 4, and so on and so forth. Example, if I do 7 squared, that's going to be 7 times 7, which is equal to 49. Nothing too crazy, but that's what squaring a number is. It's raising it to the second power, so multiplying it by itself. And this is the reason why I introduced this, because of talking about square roots. Now, if you've ever actually seen the full definition of a square root, it's actually very, very weird. And it's because the definition requires us understand like a lot of algebra to understand. But the square root, in essence, is the reverse of squaring. It's undoing the squaring process, just like subtraction is the undoing of addition. Multiplication, division is the undoing of multiplication. Square rooting is the opposite, is the undoing of squaring. So the way square roots are written is you have this little symbol, and then usually on the inside you have something. Usually for us, it's almost always going to be a number or a single variable like x squared or something. But later on in math courses, they start to put expressions on the inside of those things, and we start dealing with them that way. So when you're tasked with looking at this, you're going to ask yourself, what number do I need to square to get the blue box? So what number do I need to raise to the second power to get what's on the inside of the square root? That's what square rooting is is done. If you want the formal definition, it's actually like, I'm going to write it out for you while you're writing this. You do not need to write this down. This is the formal definition, is that x is the square root of y if x squared is equal to y. That's what it means. And that's what we call a recursive definition. And if there's any people out there that like computer science, recursion is always one of those funky things. It's very, very annoying. So that's the formal definition, which is not very approachable at all. So that's why I'm not writing the formal definition. But to give you some examples, which you may like, if you've already seen this stuff, great. If not, also great. So the square root of 9 is equal to 3, because if you square 3, you get 9. The square root of 121 is equal to 11, because 11 squared is 121. So it's undoing the squaring. So you're trying to find a number that when you square it, you get the inside value. Now, one of the problems with it is that not all numbers, like what I've just given you are two examples of perfect squares. Numbers that when you take the square root, you get a whole number. So 25 is a perfect square because the square root of it is 5. 36 is a perfect square because when you square root it, you get 6. But if I were to give you something like the square root of 152, this will equal, I don't know because I don't know what 152 is off the top of my head, is 12.3288 on forever. It's an irrational number, not meaning that it's not, you can't reason with it. That's not what irrational means in this context. It is a number that irrational numbers versus rational numbers. Rational numbers are either they are either finite numbers or they have a non-ending but repeated decimal expansion. So like 0.3 repeating. That is an irrational number. Whereas irrational numbers are numbers that go on and on forever and have no repetition. Like if you do 1/7, right? 1 divided by 7, that's a rational number. And it goes 0.142857, 142857, 148257, on and on and on and on forever. Whereas this one, you could never write out the entire thing. It would go on and on forever, and you would just waste your life. Which is what doing math does. No one should be a math major. It's not worth it. This right here is not a perfect square. And so when we're writing it down, we're writing an approximation. And this is just something for you guys to ponder over the weekend. How does our calculator figure out what the square root of 152 is? How does it figure it out? Magic? Is there a little gnome inside this that's just pumping out numbers? It's a good question. There's actually a lot that goes into calculator computations. It's pretty fun. So back in my day, we had a book And in the back of the book, they had they had a bunch of common square roots and logarithms and stuff. So you had to look at an index to figure out what those approximations were. So my mom still has a textbook that showed that. It had like a packet at the end of all the different square roots. So anyways, I'm getting sidetracked. So the main reason why I'm bringing up square roots at all is for a thing called the square root property. And so I'm going to put this in quotation marks because I can't physically bring myself to write it without quotation marks, because what I'm going to write is technically not true. It is not 100% true. So the square root of x squared is equal to x. Now, the reason why I've put it in quotation marks is because in case there is a secret agent out there, a person who's a teacher at like UNLV, or like maybe one of you guys is a math teacher at UNLV or Nevada State or something like that, and you're trying to get me fired. I don't know. But there is a thing here. Technically speaking, the square root of x squared is equal to x or negative x. Technically speaking, there are two solutions. And the reason for that, imagine, if you will, this is like, if I were to claim that this is true, if I'm not writing quotation marks, if I'm doing this, and you don't need to write what I'm about to write now, right here. So you don't need to write that. If I'm claiming this is true, this should be true for all x values, correct? But what if I plug in x equals -5? Then I get the square root of -5 squared is equal to -5. Replacing x with -5, but this would become the square root of 25 is equal to -5, but the square root of 25 is +5. And that's not true. That is why the square root is either positive x or negative x, technically speaking. Now, that is something that is purely mathematical in nature. We don't usually, so I'm going to elaborate here. But we'll only be using this in situations where the negative answer, the negative x answer, will be irrelevant. So to elaborate what's going on here. So we're going to just use the fact that the square root and the square undo each other. If you're looking at these things as purely mathematical objects, not without anything other than just math, then there are two solutions. There's a positive x and a negative x. However, the way we're going to be using it, and the way that pretty much the only way you're going to ever see it in your life, really, is going to be in a physical, like in a physical thing. And we don't really deal with negative quantities in real life, right? You can't have a distance of -5 feet. That's not real. You can't have -5 seconds, right? This isn't Back to the Future. So we will not be worrying about that case, because everything that you're going to experience, unless you decide to go further on in mathematics than this course, you're never really going to see a situation where you're going to have to deal with a negative x. It's always going to be real life quantities where the negative answer isn't useful. So does that make sense? So we're just going to use it as that, knowing that on the side, technically speaking, there is also a negative answer. The point of this is that we can take the square root of both sides of an equation, and it remains balanced. We can take the square root of both sides of an equation and it remains balanced. And that's what we're going to use it for. All right. So let's look at some examples of how to use the square root property. So example, solve for x. And part A is going to be x squared equals 64. And part B is going to be x squared plus 19 is equal to 44. Solution, part A. So we got x squared equals 64. There's nothing to do. The x is already by itself, but we want to solve for x. We don't want to solve for x squared. So we have to undo, just like we would do with the add, like if you're adding something, like if it's x plus 5, you have to subtract 5, you have to undo the addition. We have to undo the squaring, which we'll do by taking the square root of both sides. We'll do this. And so that cancels the square. And then x is equal to the square root of 64, which is equal to 8. 8 is a number that when you square it, when you raise it to the second power, you get 8. Now, because we're going to be dealing with a lot of real life situations, it's very rare that you're going to get perfect squares. So please feel free to use your calculator to find the square roots. You don't need to memorize them. I only have them, a lot of these memorized because I had to do them for so long. I know a lot of my perfect squares. But I don't expect that of you, and I encourage you to not waste brain space on it. It's kind of a useless party trick. I've tried bringing it out at parties. It does not get you, dates. Just letting you guys know in advance. But either way, part B, x squared. I just charged you. X squared plus 19 is equal to 44. All right. On this one, x squared plus 19 is equal to 44. We've got, this is a two-step equation because we have to get the x squared by itself. And like, so which thing should you take care of first? Should you take care of the square root? Like should you take care of that squaring or take care of that 19? And that's where that whole party analogy kind of works out. The square is closer to your x, is closer to your house. They're your buddies. So you know they're going to help you. So don't worry about getting them out of the house first. Worry about the other people first, the people that don't care, that are just there to party and don't really care about the person hosting the party. So we're going to get rid of that 19 by subtracting 19 from both sides. And so this is showing you that little arithmetic trick that I did. I'm just going to add 1 to both of these things in my head and do 45 minus 20. Add 1 to 44, get 45. Add 1 to 19, get 20. And subtract that. So that gives me that 25. So x squared is equal to 25. Do you need to do that? No, you don't need to do that little trick. It's just fun. It's a fun thing that you can do. Make your life a little bit easier. But if you have a calculator, do it. Yes.
Can you actually explain how that works?
Absolutely. Absolutely. Love that question. So it doesn't really make sense when you look at it like this, why it works. But let's look at it linearly. So would we all like, this is a very, I'm glad you brought that up. This is a very classic math trick. So instead of writing it out vertically, I'm going to write it out linearly. Like this. Now, would we all agree that if you add 0 to anything, it doesn't change anything? Right? So what I could do is I could do 44 plus 0 minus 19. That's the same thing, right? Adding 0 doesn't change it. And would we further agree that adding 1 and then immediately subtracting 1 will do nothing. Right? If I add one and then subtract one, it doesn't do anything to the problem. So that's what we call cleverly adding zero. If you add something and immediately subtract it, that's called cleverly adding zero. It's one of the most common tools that mathematicians use. That's like their screwdriver, essentially, in their toolkit. Now, this is something that we haven't talked about, which is a concept of factoring. But what I'm going to do is these two terms are both negative. So I'm going to factor out the negative out front. And then this becomes 1 plus 19. So I've added 1 to 19 and I've added 1 to 44. So that's why it works. Like all this is a string of equalities. So that's as long as when you write a string of equalities, what you're saying is that all of these things are the exact same. So 44 minus 19 is the same thing as adding 1 to 44 and adding 1 to 19. And you could further see it, like we could go in the reverse direction to verify it. 44 plus 1 minus 19 plus 1. If I distribute the minus sign, I get 44 plus 1 minus 19 minus 1. You see that the ones cancel. There are many other proofs as well, by the way. But these are my two go-to ones. So it's a very, very nifty trick. Does that help? Yeah. Thank you for asking. I love proving stuff. Is it all right if I delete it though? All right. So to do this one, now that we've got it, that x squared is equal to the 25, we'll take the square root of both sides to cancel the squaring, and you get the x is equal to 5. But please feel free to use your calculator. I don't expect you to waste precious brain space on knowing your perfect squares. It's way more important to memorize all the words of the Big Mac song, or any of those other things that are useless pieces of information. All right. So with that out of the way, let's actually talk about right triangles. There's a reason why we've been talking about squaring. So we already mentioned right triangles in section 1.3, right? A right triangle is a triangle that has a right angle in it, right? But now let's get some particular terminology about the right triangle. So I want you to just draw a right triangle. So we have the little right angle right here. And I'm going to color code it, but you don't have to, if you don't want to. So when you have a right triangle, you actually name the sides to be certain things. The longest side, the side that is opposite of the right angle. So if you shoot out directly from the right angle, the side that is opposite to it is always the longest side, and it is called the hypotenuse. I don't know why mathematicians decided that name. There's a really, really stupid joke I could say, but it's a little bit, it involves things that probably should mention. But it's a play on the fact that it's hypotenuse. It's a dumb joke. I'm not going to say it, but whatever. Maybe if I pause the recording. But the side that is the longest is always called the hypotenuse. I wish they had written it if they had chosen a name that was something shorter. So writing out hypotenuse is always way too long. But either way, the other two side lengths, the shorter side lengths, the ones that touch the right angle, those are called the legs. So once again, the leg is equal to a side touching the right angle. And the hypotenuse is equal to the side that is opposite to the right angle. it is also the longest side. By default, by construction, because the right angle will always, the side length that is spawned from the right angle will always be the longest one because it's the biggest angle that you'll see on the triangle. So those are the two, that's the terminology, is the two legs and the hypotenuse. And that's specifically for right triangles. Anything else, we don't use the hypotenuse. Hypotenuse is only for right triangles. And so that gives us one of the most important theorems in all of mathematics, arguably. Oh, and my pen is dead, so we'll just have a fun little get together for a second. Hope everyone's week is going well. Say something, but I'm running out of ideas, so I'm just stalling. So we have one of the most important theorems in mathematics, which is the Pythagorean theorem. From the Greeks, specifically the Greek mathematician Pythagoras. Now, what we're going to be writing down, the theorem for it, is a much more approachable and understandable way, but the original version of it. So we're going to draw a triangle. You've probably already heard of this, and if you have, awesome. If you haven't, no big deal. That's what we're here for. But we're going to label the legs A and B. And we're going to label the hypotenuse C. The Pythagorean theorem says that if you have a right triangle, then A squared plus B squared is equal to C squared. And just to gush about how far we have come as a species. So the original way, the way that Pythagoras worded this, granted, it's in Latin. The translation is that the sum of the squares of the legs is equal to the square of the hypotenuse. That was the theorem. There was no A, B's, and C's, and that's because in the time of the ancient Greeks, they hadn't thought of algebra. They didn't know about algebra. They didn't think about defining variables. That wasn't around back then. So they were doing geometry without any algebra. In fact, algebra actually comes from the Middle East specifically. Because algebra actually comes from it stems from an Arabic word, and I don't want to bastardize it. I don't know. I can't pronounce it correctly. But algebra comes from, I think if I was to try and say it, I think it's algebra or algebra. Something like that. I don't know exactly, but so the Middle East, the Middle East was the ones who discovered algebra, despite what many textbooks will have you believe. But this is a much more succinct way than the way Greek mathematicians had to explain it. They had to say it out in words, and it was awful. Now, who wants to see a proof? There we go. There we go. Excellent. So you do not need to write this down, nor do I expect you to, and you are not going to be tested on it. But I wanted to show you, we should always be questioning what you're learning. Like, right. We're not going to be running around like Patrick and the Q-tip going, because you told me to, right? Love that. I love that. Love that episode. Very, very good. Makes me laugh as a teacher because like just do it because I said so. There's a reason for why everything works. And this is actually a really, really cute proof of this. So what I've done here is on the left-hand side, I've constructed a rectangle by taking all four of these triangles and arranging them in a certain way. Now, all of those are right triangles of the exact same size, right? If I take this, you'll see that that's how I fit it there, and then I just rotated it then put it here, then rotated it, put it here, and so on and so forth. And these are all the same size triangle, right? So let's just label them like their sides A, B, and C. A and B being the legs, and C being the hypotenuse, right? So then this is our, let's rearrange it. I mean, it doesn't really matter. I think it's just more presentable if I make the long side. This is B, A, and C. So I'm going to color code these. So this is B, this is A, and this is C, right? And that's a perfect square in the inside of that, right? Because all the sides are C. Right? So what is the area then of this purple square? If side lengths are C and the area of a square and like rectangle, length times width, but with a square, the length and the width are the same, the area of this thing is C squared, right? So, and then like, don't worry about the area of the full rectangle. We don't really care about it. But what we're going to do now is imagine instead, imagine that this square that I have, I've put those little triangle cutout pieces on there, like tangrams, if you guys remember those things. You guys remember tangrams? It's like you were given a blank shape and you had to take all the little shapes that you had to make something. It's awesome. Loved it. I have a set that I'm going to give to my son very soon, and I'm very, very stoked for it. But what I'm going to do is I'm going to take this little piece and I'm going to put it right here. So I'm lifting off those triangular pieces, and I'm instead going to put them together like that. And then I'm going to do this one down here, and this one right here, right? Now, remember, this is the exact same rectangle, right? If I put this over it, it's the exact same thing. All I've done is I've just taken the triangle pieces, which I'll color in blue. I've taken the triangular pieces and I've just kind of rearranged them so they're nice and neat. Now, I'm going to color code this again. So I've taken that area, that purple area, and I've split it into two little tiny squares, right? Let's color one of them red and one of them green, right? What is the area of the red square? Remember those triangles, they still have those measurements, A, B, and C, right? So let's just kind of label it A. I'm on highlighter now. A, B, and C, right? So what is the area of the red square? A squared, right? So one side is A and the other side is A. So the area here is A squared, and the area here is B squared. And as we said, remember, this area is equal to the big area. I haven't done anything magic. I haven't changed the size of anything. All these things are the exact same. So what we're saying is the area of the green plus the area of the red is equal to the area of the purple. And the area of the green is, of course, I should have done it. I'll just do it a little bit differently. I'm going to flippy flop these ones. No. Just so I get it perfect instead of being just off, like slightly off. The area of the red is A squared. The area of the B is B squared. And the area of the purple is C squared. Boom. Proof. Done. As the mathematicians would say, is QED. QED, which is quotes estetarum, I think, which is Latin for that which is shown. So that's what mathematicians would love to write QED at the end of a proof, just to signal back to their Greek roots. But that is the proof of it. There are actually hundreds of proofs. I think mathematicians are running out of things to prove. So they're just trying to find new and fun ways to prove things that they already know. So if you want to go on a little Wikipedia deep dive this weekend, just hanging out with your friends, go ahead and search the Pythagorean theorem. It's a good read. You'll see that they have like 80 million proofs of this. There's geometric proofs such as this one. There are algebra proofs. Apparently, President Garfield actually wrote a proof of this at one point. Strangely enough, I did not know that actually until today. But pretty cool. So yeah, that's why it works. There it is in pure geometry, showing you that there is a justified reason why things work. Anyways, so now let's actually use it. What I want to do beforehand, though, notes. Part one is this only works for right triangles. This only works for right triangles. As soon as it's not a right triangle, Pythagorean theorem goes out the window. Now, a student may ask, hey, Phil, what about other triangles? I'm glad you asked, Mr. Student. There actually are different rules to find side lengths and things like that. There are various versions of it. One of them is called the law of cosines, which is a Math 127 topic, so we won't be going over it, but there are ways to find side lengths of non-right triangles. And the common ways are either the law of sines or the law of cosines. Very, very cool stuff, but not for us. Two is that it does not matter. I guess let's embrace the contraction. It doesn't matter which leg you make A/B. It doesn't matter which one you designate to be A and which one you designate to B. You can make your vertical one A and your bottom one B, or vice versa. It doesn't matter. But what is important, so big red baboon butt, but C is always the hypotenuse. C is always the hypotenuse. C is always the one that stays by itself. So it doesn't matter which one you make which leg you make A and which leg you make B. That doesn't matter. But C is always the hypotenuse. So let's go ahead and do some examples. Example. Find the missing side length. We're going to do two of them. And if we have time, we'll do two. And then the other two are going to be done through word problems. So we'll do this one. So it's going to be 9 on the base, 12 on the vertical, and then X is the unknown. And then part B, we'll do one in a slightly different orientation. And I'm going to make sure I mark that this is a right triangle, because otherwise we wouldn't be able to do the Pythagorean theorem. Unless it's implied. That's why the right angle is there, to imply that this is a right triangle. For this one, we'll do the horizontal is X. The vertical will be 3, and the hypotenuse is 7. So we'll solve these two. Well, not solve them. We will find the missing side length. So with part A, if it helps you, some people like to label them A, B, and C right off the bat, and that can help you. As you get better at this, you don't need to do that. But from the start, label the legs A and B. It doesn't matter which one. I'll make the vertical A and the horizontal B. And then your hypotenuse is always C. So that's your A, your B, and your C. So the Pythagorean theorem says A squared plus B squared is equal to C squared. So A squared, 12 squared, plus B squared, which would be 9 squared, is equal to X squared. So we got to compute this into our calculator a little bit. Or if you know your perfect squares, that's great. But this is 144 plus 81 equals X squared. And then we can simplify the left-hand side a little more. That's going to be, I can take away one from both of them and then add them together. And you should get, oh, no, not take away. Not I'm thinking about subtraction. I'm going to add the 80 and then add the 1 to get 225. Is X squared. And if anybody knows that's a perfect square, that should be 15. Because we don't want to solve for X, we want to solve for X squared. We don't want to solve for X squared, we want to solve for X. So we'll take the square root of both sides. What color you guys want me to use? Let's use some lavender. Let's get some prettiness here. And get that 15 is equal to X or X is equal to 15. I don't care either way, it's fine. And yes, technically these are measurements, so there needs to be units described, but we don't really need to because there's no units mentioned. If it is said feet, we write feet, but no units were described, so we're good. Any questions on that? Yes. I will, yes. Yeah. Thank you for letting me know. In the future, if you need to get going, anybody you can leave if you need to get going. If there's something you need to do. But thank you. I will be posting this probably about an hour after this. Yes, you as well. All right. So part B. I'm no longer going to be labeling the A's and the B's and the C's, but if you want to, if that helps you, please continue to do so. But I'm going to do leg squared plus leg squared equals hypotenuse squared. So one of the legs is X, the other leg is 3. So we can write X squared plus 3 squared is equal to 7 squared. But you could just as easily have written 3 squared plus X squared is equal to 7 squared. Either way is fine. It doesn't matter which leg you put first. That's going to be X squared plus 9 is equal to 49. And so this is a two-step problem. We first need to subtract 9 to get the X squared by itself. X squared is equal to 40. And 40 is not a perfect square. So we'll take the square root. Unless otherwise specified, by the way, round to 2 decimal places. It's usually enough. So we'll take the square root of both sides to get that X, that square to cancel. And you'll get the X is the square root of 40. Which is equal to 6.32455. On and on and on forever. So if we're going to round to the nearest hundredth or second decimal place, we'll get 6.32. Whatever. I'm not going to spend some. All right. Any questions on that? All right. And don't worry if you want more practice, we are going to do 2 examples that are real world examples, quote unquote. So we'll be doing it just in a real world example. So the question is, have you guys, oh yeah. Have you guys ever like bought in a TV and it says it's a 50-inch TV? Have you ever measured it to make sure that they're not lying to you? You should, because if you measure the horizontal, it won't be 50 inches. Do you know how they define that? They're talking about the diagonal. So when they say this is a 60-inch flat screen, they mean the diagonal from one corner to the other. That's 60 inches. That's what they're saying. So you don't get berate like so. If next time if you work at like Best Buy or something like that, and someone berates you, says this isn't a 60-inch TV. No, it's a 60-inch diagonal. That's what that's saying. But 60-inch diagonal TV doesn't have the same roll off the tongue. It doesn't sound as appealing as a 60-inch flat screen. So, anyways, now you know whenever you're talking about screens, they always measure the diagonal to determine them. So a 51-inch TV has a height of 25 inches. Phoenix, not the city, but a guy named Phoenix has a TV stand that is 20 or 42 inches wide. Will the TV on Phoenix's TV stand comfortably? And so I'm going to add in that comfortably because technically speaking, it will fit, right? Like, just like everything can be a hammer at least once, like you could fit it on top of it, right? You could fit it on top. It just might not look nice. So what I mean by fitting comfortably is, does it spill over the sides or does it fit nicely on top of the TV stand? Or does Phoenix need to go out and buy a TV stand as well? So by the way, just this means the diagonal is 51 inches. You can put that above the problem statement or below it, whatever you want to do. That's what they mean when they say a 50, like X inch screen. They're talking about the diagonal. So me personally, I like to draw pictures whenever I can. So we got our nice little flat screen TV that we just bought. And it's got little legs here, right? And then we've got our glorious little brown TV stand. There we go. And so the TV stand is measuring 42 inches wide. So this distance right here is 42 inches. We know that the height of the TV is 25 inches, and we know the diagonal is all right. Is 51 inches. And then the unknown thing is the base. We don't know the base. I don't know how we know what the height is. Don't question me. Just assume that they mentioned it at the store, but they didn't bother to mention the base. I don't know. So we'll call this X, I guess. And we're gonna ignore that my voice cracked. Phil, you brought attention to it. Yeah, whatever. Okay. Thank you. That's what exactly. We didn't notice anything. Be like Dory and just forget that this thing happened. So we have a right triangle then. We have an inscribed right triangle right here. Right here. So we can use the Pythagorean theorem. X squared plus 25 squared, the leg squared plus the leg squared is equal to the hypotenuse squared. And then we can solve this. Yeah, the numbers are a little bit larger, but larger numbers are just people like you and me. You don't need to be afraid of them. So x squared plus 625 is equal to 51 squared, 2,601, right? And we want to get the x squared by itself, so we'll subtract 625. And get that x squared is equal to, please feel free to use your calculator, 1976. That's about 20 years before, after I was born. Cool. Right? Believe that. Yeah. I was born in 1956. If only. Anyways, I always want people in. I'm not as old. I'm not as young as I was. The students have started asking my age because they always wonder how old I was, and that's started to stop, and that's sad. It's the gray hair. Anyways, we're gonna take the square root of both sides and cancel it. And get x is equal to the square root of 1976 is 44.45 inches. 44.45 222 on and on forever. But if we're going to approximate to the nearest hundredth or second decimal place, that'll be 44.45 inches. But that's not the answer. The question was asking, will it fit comfortably? And it will not, because it's larger than the TV stand. The TV is wider than the TV stand. So it will not fit comfortably. Does someone else have to say comfortability, like to write comfortable? Comfortability.
I used to.
So that is the answer. The answer is that. You recognize that as a rectangle. Interesting little program. All right, and let's see at the time. All right, so we'll do this last one, and then we'll start up a little bit. So example, unless there's any questions on that one. Yes. I will be, yeah. I'll be posting the recorded lecture archive to the recorded lecture archive. So on our Canvas page, there's a bunch of tiles, and then below that, there's a couple. There's like syllabus quiz, online etiquette, and then there's one last one that says recorded lecture archive. So click on that, and you'll be able to get to all the recorded lectures.
All right.
Of course. So a ladder needs to reach the top of a 15-foot building when it is 7 feet away. What is the minimum length of the ladder? So maybe you might be wondering, why am I saying the minimum length of the ladder is for any of those smart Alex out there and say, just grab a 100-foot ladder. It's guaranteed to work. Or a 15-foot ladder. Yeah, I have a little book that I got when I declared that I was a math major that my parents got me. And it's all these funny answers to math problems. So it's like expand x plus y squared. It said expand this. And the student wrote, and so hilarious. So just in case there's any cheeky people out there trying to say like, oh, well, you could just use a 15-foot ladder and that'll definitely work because it's the same height as the building. Yes, but I want to know the smallest ladder that can be used. If that was the problem and I didn't specify minimum, that is technically answering the question, so I would have to give full credit. So I'm going to draw a cool little building. Got a cool little sign. They got one of those cool ones, this neon, and then maybe they have a revolving door. Maybe they're one of those cool people. But anyways, the height of the building is 15 feet. And then we've got this pink ladder that we want to put up so that it barely reaches the top. Oh, and then the base that has to be 7 feet away from the bottom. And we're assuming this makes a nice right angle so that we have an inscribed right triangle. With 15 feet being one of the legs, 7 feet being the other, and then the ladder ends up being the hypotenuse. We'll call it, what letter you guys want to use? X. X is fine. You can use whatever variable you want, though. I'm going to use it in lavender. So, hypotenuse squared, leg squared plus leg squared is equal to hypotenuse squared, so we can solve it that way. 7 squared plus 15 squared is equal to x squared. And that means, so that's 49 plus 229, plus 225 equals x squared. 49 plus 225 is 274. And then we'll take the square root of both sides to solve for x, just like normal. That cancels the square root. And then, so the square root of 274, we get that x is equal to 16.5529, but we're going to round to the nearest second decimal spot, nearest hundredth. So we're going to get 16.55 feet. Now, that is the answer that, like, if this was a problem on your homework, that is the answer they'd want because the question would ask round to the nearest hundredth. But why is this not technically correct?
You have to specify that it is for the building.
No. It has to do with what I did when I rounded. I rounded down.
Yeah, I've noticed those like.
So technically speaking, by rounding down, this ladder actually won't reach that far. It had to be exactly 16.5529 on and on forever in order to reach the top of the building when it's 7 feet away. So this one won't actually reach the top, technically speaking. Now, our problems would, like, if that was to ever happen, it would probably tell you, the problem would tell you to round up. So like round up to ensure that it is long enough. I don't foresee that being an issue. If it does ever happen though on your homework or quiz or exam, let me know and I will give you full credit back, because that shouldn't happen. But just being completely transparent here, technically speaking, we want a ladder that is larger than 16.5529, so on and so forth. So a 17-foot ladder would do the trick. So let's see here. We got 5 minutes. That is fine. I'm going to just write down the next part of it. We're going to talk about trigonometry now, unless there's any questions on any of this. So trigonometry. Honestly, one of the coolest areas of mathematics in undergraduate work, in my opinion. If you ever get the chance to take Math 127, I really, really recommend it. It's a very, very fun course, especially if you take it from like my wife. She is great with trigonometry. She loves teaching it in a very, very particular way that requires very little memorization and more deduction and building up those axon connections in your brain. Great, like it's one of the it's such a good scratch at your brain. It's very, very fun. So I highly recommend it. We're going to be going over just the basics. So in general, so some jargon / notation. We for triangles, angles are written with uppercase letters and side lengths are written with lowercase letters. So like mathematicians, we tend to have no consistency in our notation at all. But one place that we have kind of sort of agreed for the most part is that uppercase letters are devoted to angles, lowercase letters are devoted to side lengths. Just letting you know that so that when you see a picture, you know what the A's and the B's and the C's mean. So lowercase letters, side lengths, uppercase letters, angles. In particular, we don't want to just go around willy-nilly labeling them A, B's, and C's, and D's, and E's, and E's, like whatever. We want them to kind of correspond in a certain way. So side length A, side length lowercase a, is opposite to angle A, angle capital A. Same thing with B to angle B, and side length C to angle C. So we're going to draw a picture of a triangle to showcase how this works, and then that's what we're going to call it for today. I'm sorry to kind of rush at the end here. I just don't want to keep you guys late. So I'm going to label these A, B, and C. So that is like the bottom left. This angle is angle A. This angle here is angle B. And this angle here is angle C. If you want to know the side opposite of it, just draw a line straight out from the angle, and that will give you the opposite side. So starting at C, the opposite side will be right there. So that should be the side labeled C. For B, we'll just draw a line outward of it. So this is side B. And last but not least, that is side A. So it's going to be very, very important. And the reason why it's going to be important to know which side is opposite has to do with how trigonometry is developed. Trigonometry is defined by opposite side lengths and adjacent sides. We haven't written what adjacent sides are yet because we'll cover that on Monday of next week. All right. All right, guys. If you have any questions, feel free to email me. Otherwise, you guys have a lovely rest of your week and a great weekend. And I will see you guys on Monday. Okay. All right.